chapter 6. Momentum, collision, momentum, impulse, and collision. Collision, okay. So as I said, this is another chapter of advanced stuff. Similar to energy, it's basically give you some new concept, introducing some new concepts, and which is useful in certain situations. In this case, specifically, the concept of momentum impulse are very useful to talk about collisions, okay? Well, collision is one kind of phenomenon we have in our everyday life. Sometimes you see the collision of cars. There might be a collision of people, especially if you play football. There's a lot of tackling there, right? And then there's all kind of other collisions. And in general, you can think about any two objects that get close to each other, close enough, they interact with each other, you can call it a collision. So in this sense, collision is really kind of a general, you know. So in this chapter, we'll develop some useful concept to learn, to know, which will simplify our problem solving for in mechanics. So let's start from momentum directly, okay? Again, this is the word that we use in our everyday life, especially regarding to sports, right? Like for example, they may say, this team got some momentum, or this specific player lost his momentum, so he wouldn't be able to do it very well or something. But in physics, that's a specific meaning, okay? So in physics, we use P for momentum, and then it's defined as mv, okay, mass times velocity, okay? So because velocity is a vector, so the momentum itself is a vector as well, naturally, okay? So a P equal to mv, okay? This is the mass, this is the velocity. So mass times velocity, okay? And based on definition, it seems a pretty easy concept to understand, right? But again, as far as the object is moving, there is some momentum, you know? And the bigger the mass of the object, the bigger the momentum you have, okay? Which actually makes sense, because you probably feel like, I don't know whether you guys play football. I don't play football. My son plays football a little bit. And so if you have a collision, I mean, if you collide with somebody else, right? The other person, for the same velocity moving, you feel like the impact's bigger if the person is heavier, you know? And that's exactly because there's a bigger mass here. So a mass times velocity here, okay? Now, notice in the previous chapter, we talked about kinetic energy, right? Which is also kind of related to mass and velocity. In there, we have this combination here. Well, they're kind of similar, but they're not the same, okay? For one thing, clearly, there's no 1/2 here, and there's no power 2 here, right? And for another thing, because, see, here we're talking about velocity, so, well, here we're talking about actually the speed squared. So this is, kinetic energy is a scalar. Well, momentum is a vector. So because v is a vector, so there is a direction with associated with momentum, okay? Well, does that mean that this chapter is going to be as challenging as chapter 4? No, okay? The reason is mostly in this chapter we'll stay with one-dimensional motion, okay? The objects stay along this a single direction. The reason for that is for 2D or 3D motions, we can still use momentum stuff, but it's going to be pretty complicated. So we won't get there, okay? So we'll mostly stay 1D case, so we don't have to worry about too much of the component and everything. So this is a vector. Well, what about the units? Okay. Take the unit of mass times unit velocity. You have kilogram times meter per second, okay? And that's the unit of momentum, okay? Pretty easy. And in this case, nobody claimed this unit with this name. So we just, this is just it, okay? This is just kilogram times meter per second. That's it, okay? There's nothing else, okay? Okay, now why is the momentum useful? Because we actually can derive something called let's talk about impulse momentum theorem. Okay. Okay, so let's start from our old friend of Newton's law. Okay, so you have a force, total force equal to mass times acceleration. Okay. Now consider, so what is the acceleration here? So in general, the acceleration you can define it like for a short amount of time, it'd be equals to change of velocity divided by change in time. Okay. So we write our acceleration using delta v over delta t, right? We got this one. Okay. We got this. Now let's say, so let's multiply delta t on both sides of this equation. Then we have f delta t equals to m delta v. Okay. And we define something called impulse, okay, equals to f delta t. Okay, this is our impulse. And this on the right-hand side, you can write like, because m normally is a constant, so m delta v normally can be, you can write this as delta mv together because m is a constant, and that's nothing but delta p, okay? So basically, we can rewrite this formula as I equals to delta p, okay? And this is what we call impulse momentum theorem. Okay. Now you may say, there's nothing new here. We derive it, we just rewrite it, our Newton's law using this different combination. That is true, okay? So in some sense, it is not a new law we have, okay? It is, in some sense, it is a just different version of Newton's law. Another way to write this thing here, F equal to m delta V over delta T, is if you put m in there, you can write as, you can write F equals to delta P over delta T, okay? And that's another version of Newton's law. So Newton's law can be written like this, or it can be written as this, okay? So there are different versions of Newton's law. So in some sense, this impulse momentum theorem is another version of Newton's law, okay? So it's not like a totally new, it's just coming from Newton's law. It's basically redefined quantities in Newton's law, but it just turns out, again, it's kind of convenient to have these quantities introduced, especially when you consider collision. And also, as we see later, we'll have something called conservation momentum, which also is very convenient to have, you know, to be used in doing a lot of stuff. So let's go directly to a example for using impulse momentum theorem to solve problems. Okay, so that's going to be our okay. Let me in this chapter. Okay, let me go. Okay, so let's do the this is the collision test example. Okay, let's use that example here. Okay, so in this example, what is given is basically in this picture. So you have a car with mass of 1.5 times 10 to the third kilogram, and then making a collision to a wall and then rebound it. Okay, so the initial velocity before the collision is negative 15 meter per second, and then the final velocity after collision is 2.6 meter per second. Okay, now it also tells you that the collision process itself lasts 0.15 seconds. Okay, so ask you what is the impulse coming from the car due to collision, and then the magnitude and direction of the force on the car. So let me write everything here again. My memory now is really short, so let me bring this closer to us. Okay, let me bring right here. Okay, maybe even more closer. Okay, so let me draw this. So this is example 6.2. No, not this one, but this one. Collision test. Okay. So again, we have this car collision with a wall. I'm drawing things really bad here. So what we're given in the problem is before collision, the car goes towards the wall with velocity of negative 15, and then after is a positive 15 meter per second. And after collision, it goes back is positive 2.6 meter per second. Okay. We're also given the mass of the car to be 1.5 times 10 to the third kilogram, and then the collision time is 0.15 second. Okay, the first question we want to know is the impulse on the car. Oh, wait, not impulse, but impulse. I don't know. Impulse on the car. And then the second question is the average force from the wall. Okay. Well, this is also from the wall. Okay. Okay, let's do this. Okay, how do we do the problem? Okay, again, for all the problem we do, we start from the unknown here, right? Normally, this one asks about impulse, so we need to go to the impulse. So what do we know about impulse? We just learned it. There's two things we know. One is that we know the definition of impulse is given by force times time, like right here. Hold on, where's mine? Yeah. The second thing we know is there's a relation between impulse and momentum change. So there's two things we know. Well, we can only solve the problem with one of these two, right? Let's try this one. Okay, this one won't work because we don't know force. Okay, so force actually is what's asked for the second part, so we cannot use this one. That means we need to use this one. Okay, so we can use impulse equal to momentum change. Well, we know the initial velocity and final velocity, and we know the mass, so we can figure out momentum change. So let's use the second formula to calculate the problem. Okay, so let's try to calculate momentum. The initial momentum pi equal to mvi here. Okay, well, they're vectors. You can put the arrow on top of them. So what is the initial velocity? So, well, as we given in the problem, it's negative 15, and this is a positive 2.6. Again, because they're vectors, it's important to realize they can be either positive or negative. And then in this problem, actually, it's defined the positive direction to go to the right. So this one is negative, right? So if you plug, you can plug in the momentum here to get your initial momentum. Okay, so it'll be like 1.5 times 10 to the third kilogram times negative 15 meter per second. Okay. Well, just calculate this. 15 times 15 is 225. So 225, but there's a, so it's actually if you put this like this will be 10 to the second. So so it'd be like if you put a 2 decimal places, it'd be 10 to the fourth. Okay. So it'd be like 2.25 times 10 to the fourth kilogram times meter per second. Okay. With a minus sign here. Okay. Well, the final momentum similar is going to be mvf, which is a 1.5 times 10 to the third kilogram times positive 2.6 meter per second. Okay. Well, I don't know what is 2.6 times 15. I guess I can. I mean, basically 2.6 plus half of that, 1.3. So that's like 3.9. So 3.9 times 10 to the third kilogram meter per second. Okay. So that's the final momentum. Okay. From there, we can figure out the moment for impulse, which is just change of momentum, which is final minus initial. Okay, you have 3 point. Okay, here's the thing. You have a positive number minus a negative number, right? So you have to keep the sign of everything. So I have 3.9 times 10 to the third minus negative 2.25 times 10 to the fourth, okay? So you need to keep the minus sign here, okay? So that's equivalent to say 3.9 plus, okay, let me put one here, so 22.5 times 10 to the third, okay? So that's gonna give you 26.4, okay, times 10 to the third kilogram times meter per second, okay? Or 2.64 times 10 to the fourth kilogram times meter per second, okay? Notice that impulse, because it's directly related to momentum, so they share the same unit. Well, another unit you can write here is, according to definition, is gonna be Newton times second, but that's the same as kilogram times meter per second, because Newton is kilogram times meter per second square times meter, that's the same as this. So these two units are exchangeable because they're the same thing, okay? Anyway, so we got this answer, this is the part one, answer for part one. We got 2.64 times 10 to the fourth, which is the same as what we got here, okay, good. Now, what about the force, okay? Well, because we know the moment of impulse here, it seems like the force we can get directly by the definition of impulse. So just take the impulse divided by the time here, okay? So we got 2.64 times 10 to the fourth divided by the time, which is the time for the collision, which is a 0.15 second, okay? This gives us force, okay? 2.64 divided by 0.15. So we got 17.6 or 1.76 times 10 to the fifth, okay, Newton, okay. So that's the average force from the wall, okay. Well, this whole calculation is pretty straightforward. We're just basically using the definition. What I want to bring up to you is this, okay. First of all, again, everything we're talking about here are pretty much vectors. So it's important to keep their signs here. So the initial momentum is negative, the final momentum is positive. When you use final minus initial, you have to keep the sign. So it's equivalent to adding two positive numbers here. So you reach, you get a big number here, okay, for the impulse. Notice the impulse you got is positive, which makes sense because when you collide with the wall is actually giving you impulse to the right, okay? So that's why it's positive. Similarly, the force given by the wall is also to the right. So the direction of the impulse and the direction of the force are the same, basically, okay? So you got a positive force as well because the force is supposed to be going to the right, okay? Now for the momentum, right, initial momentum is negative because going to the left. Final momentum is positive because it's going to the right. So all of these things are not difficult as far as you make sure you have the right signs for these numbers, and then make sure when you calculate the change in momentum, you put the right sign here as well, okay? Now, one thing another thing I want to point out is in calculating the force, it really doesn't really save us much time by doing this new method, okay? We actually, what we can do to calculate the force is this, okay? Given the final velocity and the initial velocity, we can figure the delta V here, okay? And then given delta V, we can figure out A because we know delta T as well. And then after that, we can use F equal to MA to calculate the force, okay? So it'd be like this: 1 step, 2 steps, 3 steps to get our force. Well, to get your force this way, it's like a 1 step to get momentum change, to get momentum, 2 steps to get impulse, 3rd step to get force. It's very comparable, you know, it's not really a huge difference, okay? So we don't really save much by using impulse momentum theorem to calculate force compared with what we do with Newton's law. But we have some new quantity like impulse we can look at. This is one thing. Another thing is later on when we learn conservation momentum, we'll see that it is actually way more, a little bit easier to do it, okay, with conservation momentum. So let's talk about chapter 6, okay? So we started this chapter on Thursday, which is a while ago. So basically, this chapter is another chapter about advanced concepts in mechanics. So the concept we talk about here is called mostly is momentum, defined as m times v, mass times velocity. It's a very simple definition. It's very intuitive, and the unit is this kilogram time meter second. Okay, now we can derive something called impulse momentum theorem, which is basically rewriting Newton's law. Okay, like this. Okay, then you have this. Okay, F equal to and we also we did it like example how to calculate stuff with this impulse momentum theorem and momentum change. Okay, and that's all we did. Okay, on Thursday. Okay, so let's continue today. And as I said, this chapter is pretty short, so we might just finish it. Okay, quickly in this in today, and then we'll go ahead and do the next chapter. So, by the way, we have 3 weeks, right? Like we have this week, the full week, and then next week, and then we have another week, which is not the full week, I think. In the last week, which is the 8th week of this semester, it's only, I think the whole class end on Thursday or something, if I remember. Is that right? Do you guys know exact date of this? Yes. So I need to look it up. Is there a dedicated final time for this class, or is it up to me to choose a final time? Do you guys know? No? Okay, I'll double check, make sure. Very likely, excuse me, very likely we're going to have to do our final test on the lecture. So it seems like the plan for us now is, excuse me, we're going to have a test. So this is our 6th week, week number 6, right? This is our week number 6. So we have a test on this week, and then we will have another test either on week 7 or week 8. And then we have our final on week 8 as well. So again, as I said, everything's got more condensed because it's summer, you know. Okay, I got a message. Oh, class ends the 22nd. Okay. What day is that? Is that a Thursday or something? Let me look. 22nd. 22nd?
23rd. 23rd.
Okay, 23rd is Thursday. Okay, so it's basically what I said. So, yeah. So actually, if you think about it, there's really not much time left. Okay, we have 2 full weeks and pretty much like half a week, and that's it. You know, that's all we have. So, yeah. So everything needs to be speed up. You know, you need to try to spend as much time as you can for this class. You know, there's not much time in total we have, as I said, right? So, and then after, yeah, I think we'll either do test number 3 in the next week or the week after next. It depends on how fast we go. It might be better to do like a very early in the week 7, like maybe Monday or something. This way, you guys have a little more time to study or something. Okay. So okay. Anyway, so let's go back to this this chapter 6. Okay. So the next topic here is actually I'll call it item number 3 after impulse momentum theorem. So let me put it here. So it's going to be, okay, 3. It's called conservation and momentum. By the way, some people would call this like linear. They call this linear momentum because later on there's another momentum called angular momentum. But normally when you just say momentum, people understand you actually mean linear momentum. Okay, so that's kind of convention. So let's talk about conservation momentum, which is the most important stuff in this chapter. This is something really, really important. I mean, that's the reason we want to visit this chapter, because of this conservation law. Okay, now to see that, let's go back to our previous lecture. Look at this impulse momentum theorem. Okay, so remember we start from Newton's law like this, And then we can, if we write our expression as delta V over delta T and multiply delta T, we got this impulse momentum theorem. And actually this suggests us, okay, if you go back to this formula here, right? It suggests us to write our force, you can write the force as delta P over delta T because mass is normally a constant. So M delta V equal to delta MV, which is delta P. So let's start from there, okay? In some sense, this is a different version of Newton's law. You can write your Newton's law using this version instead of F equal to MA. Okay, sorry, delta T. Okay, so from there, we actually can derive this conservation momentum. Let's consider two objects, okay? 1 and 2, okay? Now let's say there's some interaction between them, okay? Whatever interaction it could be. Maybe gravitational attraction, or maybe electromagnetic, or maybe other like complicated force, or whatever. Let's say the object 2 exert a force on object 1. For the sake of definiteness, I'll just write the force going this way, okay? I'll call it 2, 1, okay? So this is the force given by object 2 to object 1, F21, okay? According to Newton's third law, there's going to be another force reaction from object 1 on object 2, F12. Now let's write down Newton's law for each one of the object using this form, okay? For object 1, we will have F21 equals to delta P1 divided by delta T. Similarly, for object 2, we have F12 equals to delta P2 divided by delta T, okay? So, and let's do this, let's add them together, okay? So we add these two equations together. On the left, we will have F21 plus F12. On the right, we will have delta P1 plus P2 divided by delta T. Okay. Okay, here comes the important point, okay? So what is F21 plus F12? Send me a message, tell me what do you think? Again, this is action and reaction, right? So what does F21 plus F12 equal to? Do we know this? Or if you feel like it's something we don't know or depend on some other information, you can write that as well. Okay, I got one answer, which is correct. Anybody else? Okay. Again, if you remember, yeah. If you remember, this is just action and reaction, right? According to Newton's third law, action and reaction, they're equal in magnitude and opposite in direction. So that means if you add these two forces together, you got 0. So on the left, we have 0 here. This is totally Newton's third law, okay? Now, what is on the right, okay? You can define P1 plus P2 as the total momentum of the system. So you can call it P total, okay? So what this tells you is the change of momentum divided by change of time equals 0. So how could that be? Because there's always going to be some time there, right? Like when you have interactions, that can only tell you that the total momentum itself is 0. And or you can write this like P initial equals to P final, okay? That's called conservation momentum, okay? This is the conservation law we're looking for, okay? And remember, we talked about another conservation law in the previous chapter. We have conservation of energy, right? In that case, we have total initial mechanical energy equals total final mechanical energy, like this, right? And so there's kind of a little bit of similarity here in the sense that when we solve a problem, instead of looking to the details of this system with forces and interactions and everything, we could just look at two states and then look at their energy. If the energy is conserved, we can get some information. Same thing here. If the momentum is conserved, we can get some information as well. Now, what is the condition that this conservation law holds? Okay, so there's let me give you another example here. Okay, so let's consider again these two objects. They interact with each other. Let's say this is F21. This is F12. Okay, so let's say in this case, there's some other forces, okay, some external forces applying to both of them. It might be some gravitational attraction from the Earth or something like that. I'll just, in general, I'll just write F, this is the 1 and 2, right? So I will just call this force F1 and this force F2, okay? So when you have external forces on the object, right, you can try to write Newton's law again like we're doing here. Then for the first object here, you have F21 plus F1 equals to delta P1 divided by delta T. And then for the second object, you have F12 plus F2 equals to delta P2 divided by delta T, okay? Now you can again try to add these two equations together. On the left-hand side, we'll have 4 forces, okay? So we have F21 plus F12 plus F1 plus F2, okay? On the right-hand side, we have delta P1 plus P2, okay? Just like before, okay? But there's now something becomes different now, okay? Notice these two forces, they're still action and reaction, so together it's 0, okay, as before. However, there are 2 new forces here, F1 and F2. They're given by some external objects or something. So in that case, I mean, certainly we cannot say that they cancel each other out. And in general, they do not cancel each other out, okay? So there is a total force for the object, on the 2 objects together. Well, on the right-hand side, we just have the total momentum change divided by delta T, okay? So we see that we do not have 0 on the left. So the total momentum in this case is not conserved, okay? And actually, if you look at this formula here, it's very much the same as this formula, except that we're not talking about a single object, we're talking about the force and momentum for 2 objects combined, okay? Well, that's kind of makes sense, it's self-consistent, right? Because when you have 2 objects, if you consider these 2 objects as a system, okay, as a one system, then you could say that for this system of 2 objects, it obeys Newton's law because the total external force acting on the system equals to total momentum change divided by total time, okay? So Newton's law still is correct, but there's just no conservation momentum, okay? Now from this example, we see that the condition for conservation momentum is there's no external forces on the system, okay? So condition of conservation of momentum of a system. So the condition of the conservation momentum of the system is there's no external forces, okay? No external forces acting on the system. Well, you may say this is again kind of limited, you know, it's not always conserved. Only if there's no external forces, then it's conserved. Seems like it's kind of limited, but actually turns out there are a lot of cases we can either say there's definitely no external forces, or we can say the external force is tiny, so you can ignore it. So you still, I mean, the momentum is still conserved. So while those cases, for example, if you consider the whole universe, the universe as a whole system, okay, there's no external forces acting on the universe as a whole system because the universe, by definition, includes all space and time and everything. So there's certainly no external force in that case. So we could say that the total momentum of the whole universe is conserved, okay? For example, like the whole universe. Okay. Well, that might be too much for us, and it's too big, you know. But you can also, for example, some other cases, like for example, when you have two cars make collisions to each other, like head-on collision. Okay, in those cases, there are some external forces. For example, there might be some frictions from the ground. Okay, however, if the interactions, if the collision happens in a very short amount of time, those external forces produce very small impulse to the system. And if you just consider right before the collision, right after collision, you could say the momentum is roughly conserved. Okay. Well, if you wait long enough, certainly the longer it is, the more friction will give impulse to the system or taking the impulse away. So anyway, it's gonna be different. But when you consider just right before collision, right after collision, normally you can use conservation momentum. Okay, right before to right after collision. So these cases are like actually we can all use this. Okay, and another comment I want to make here is, well, certainly when we solve problems, especially if the problem says please use conservation momentum to solve it, then definitely it means that you can use it. Okay, well, what we talk about so far is just for two objects, right? But actually it applies to many objects as well. If you have a system of many particles or something, from n from 1 to 3 all the way to n. Okay. Well, if there's no external forces to the system, there's some interaction between the system. But if you can do the same as we're doing here. We're doing here. Write down Newton's law for each particle. But because all these forces coming from other particles has a counterpart because of Newton's third law. So when you add them together, they're gonna cancel out as well, as just like in this case. Okay. So in the end, you can say that the system, the momentum of the system is conserved as well, as far as there's no external forces. Okay. So well, we're not going to talk about this. We're not going to use this complicated case in solving problem. We're mostly focusing on two objects, but that's kind of like something you can keep in mind. Okay. So let's go to a specific example here. Okay. Let me pull out the textbook. And let's go to, well, that's too much. We're doing topic 6. This is what we're doing, okay? So let's do this problem, okay? The Archer's problem, okay? Example 6.3. So what you have is there's an archer stands at rest on frictionless ice. Okay, there's no friction on here. Okay, so the total mass of everything, including the bow and the arrows together, is 60 kilogram. Okay, and then if the archer fires a 0.03 kilogram arrow, I mean horizontally in the positive x direction, what is the subsequent velocity? What is his velocity across the ice? Okay, let's just do this one. Okay, there's a B and C, but maybe I'll do B as well. Let's do A and B. Okay, then he fires a second identical arrow, same speed relative to the ground, but an angle 30 degrees above the horizontal. Find his new speed. Okay, so let's do A and B. Basically, the information we have is like 60, 0.03, and 50. Okay. So we have this is a guy. So the total, okay, so this is what the guy, I mean, stands. And then after he fires so he's on the ice, okay, on the frictionless ice. Now after, so you picturize it, what's gonna happen, right? So after he fires the arrow, right, the arrow definitely goes to the right. This doesn't seem like an arrow. Okay, maybe like this. Okay, anyway. And then, so with the velocity given, right, like 50 meter per second. What do you guys think? Which direction does the archer himself moves? What do you guys think? Or we just stand on right at rest, or he's gonna move somewhere? So tell me, what do you think? If the arrow is fired to the right, what would be the direction of this archer moving? Which direction will he move? Okay, I got a couple answers. Let's see. At rest, left, stay same. Okay, actually, we don't really know the answer, but we can solve this problem. But it turns out he's going to move to the right, left. Okay, well, this is kind of unrealistic because you never see somebody throw something on the ice and going to the backward, right? But anyway, but we will find out. Okay, so that's the velocity we want to find out. Okay, so again, the total mass is m total is, I think, is 60, right? I have really short memory now. Okay. 60, okay, 0.03, okay. So total mass is 60 kilogram and 0.03 is the mass of the arrow, okay? Arrow, 0.03, okay. So there are two objects involved in this problem. And because there's no external forces, because this is frictionless, the total momentum of these two objects should be conserved. So we can use momentum conservation to solve this problem. Now we know, let's label them. Okay, so this one I'll just call it A because A stands for arrow. For this one it's an archer, but we cannot call it A anymore because this one's already A. So let's call this one P. Okay, stand for person. Okay, so basically we can to solve the to use momentum conservation to solve problems. Again, we need to use basically this thing, right? Which is really simple like this. But that means we need to specify two states. Okay, one is initial state, the other one is final state. So this one, let's call this one initial state, and this one is the final state. Initial and final. Okay, and so what we can do then is to specify okay, let's just start from here. Pi equal to Pf, that's the momentum conservation, right? So let's write down the momentum we have at each of these two states. State before the separation and after the separation, okay? So before the separation, what is the total momentum here? What is the momentum of this whole thing before separation? Okay, what do you guys think? Okay, good. Yeah, somebody already got the answer. Yeah, 0, right, exactly right. It is 0, okay, because everything's at rest, okay? So it is just 0 in this case, very simple, yeah. Now, after the arrow is out, we know there's some velocity from the arrow, but there's also, I mean, there might be some velocity for the people as well. So for the person, so let's just call it MP, VP for this is for the momentum, this part, and then MAVA, which is the momentum for the arrow. Okay. Now in this problem, we do know VA, we know MA, and we know MP because we know the total mass. So the only thing we don't know is VP. So we can solve for VP. Okay. Now you can plug in numbers right away, but I prefer to solve VP just right here. So I mean, I manipulate the formula first. So I'm gonna have so it's gonna be like if we move this term to the left, so you have a negative MAVA equals to MP VP. Okay, and then we'll have a VP equals to negative MAVA divided by MP. Okay. Then we plug in numbers here. So for MA, we have 0.05 kilogram. Oh, sorry, 0.03 kilogram. And then for VA, we have, I mean, 50. This is VA, right? 50 meter per second. And then for MP, okay, we know the total mass is 60. So subtract that for 0.03 from it. So that's going to be the mass of the person. So that's it. Okay. Now from there we can solve for the speed of the velocity of the person. Okay. So just take 0.03 times 50. And then divided by 59.97. Okay. So we got 2.5 times 10 to the negative second, okay? Meter per second, okay? Okay, with a minus sign here, okay? So let's try to understand what does this tell us, okay? Okay, so first of all, you see there's a minus sign here, okay? Which means that the person should go backward, okay? And second of all, you see the velocity is really, really small, okay? It's like 0.025 meter per second, okay? Now, first of all, why does this person go backward, okay? Now, from the conservation momentum point of view, it goes like this, right? At the very beginning, there's no momentum at all. So in the end, the total momentum of these two objects should still be zero if the momentum is conserved, okay? Now, the arrow got some positive momentum going one direction. That means everything else, the person and the bow and everything should go backward with equal momentum. Otherwise, the momentum conservation wouldn't be satisfied, okay? So, so that explains why you have a negative sign here, okay? Now from the, if you want to go back to the force point of view, it's like this, right? When you apply force to the object, right, this object goes this way, right? That's why, because you apply force, so it gets some acceleration and then some velocity change. Well, this object would apply same amount of force on you, right? And then it's going to be going to the backward, and because there's no friction here, so you go backward, okay? Now, this is not very realistic because in reality, there's always some friction even on the ice. So even if you, like, next time you go to the ice, even you're on your, like, skating shoes or something, and you threw some object forward, you wouldn't go backward like that, okay? Because there's always friction. And see, even there's no friction, right? This velocity is really small compared with this velocity for the arrow. Why is that? Okay, because these two terms, because the initial momentum is zero, right? So these and these has to be equal. These two terms have to be equal in magnitude and opposite direction. And because the mass of the person is way bigger than the mass of the arrow, so if the mass, the velocity arrow, the velocity of the person will be way smaller than the velocity of the arrow, okay? Does that make sense, you guys? Okay. Yes, okay. Now, this thing itself, I said, is not very realistic because there's friction here. But there's another thing you probably experience a lot. If you ever, like, have shot a gun before, okay? Well, what you see there is actually something really similar. It's called a recoil, right? If you hold a gun in your hand, right? At the very beginning, just holding by you, right? Like a hand like this. Okay? At the very beginning, everything is at rest. Okay, now you pull the trigger and then suddenly a bullet goes out to the front, okay? Now you feel like a recoil from this part, okay? The gun and your hand is going backward. Right, you feel that. Either a handgun or a rifle, you put the rifle like toward your shoulder or something. Same thing, okay? This is going forward, this is going backward, okay? That is also because of the momentum thingy, okay? In this case, strictly speaking, there's a force on this whole thing. But if you consider your hand and the gun as a single object, the whole thing is going to go backward. So that's called recoil. essentially what this person observing here is also recoil, okay? and now you understand, okay, how do you reduce recoil, okay? Basically, you feel the velocity, the speed, right? So based on the same discussion as we have here, because the total momentum is conserved and the initial is 0, so these two terms has to be equal in magnitude and opposite direction. That means if you want to reduce the recoil, the speed here, you need to increase the mass of the person or the mass of a gun in this case. So that's why when you shoot a gun, right, you might thought it's easier to shoot a light gun, but it's actually the opposite. When the gun is heavier, it feels more stable in your hand, and because the mass is bigger, so the recoil speed is smaller, okay? Because the bullet speed is pretty much very similar to each other. If you shoot like a 9mm or 45, caliber, they're about the same, because this is basically limited by whatever the powder you have, okay, for the bullet, right, in the barrel of the gun. So and in that case, what really determines the recoil of the gun is the mass of the gun. The bigger handgun you use, or the rifle or something, normally the smaller recoil you feel, okay? You feel like the gun is easier to shoot because it's stable. But certainly you don't want it to be too big, right? If it's too big, it's very hard to carry it and everything. So there's a compromise here. But in general, that's the physics behind this recoil phenomenon, okay? Any questions? Okay, let's go ahead and do the second part of this problem, okay? So the second part is saying that, so fires a second identical arrow at the same speed, but this time is at angle 30 degrees above the horizontal, okay? So what is the initial speed, initial state in the second case? Well, this man is still there, right? It's still, but now it's moving with some velocity already, right? Because it's going backward with this velocity, with this one we just calculated. So this is the initial state, okay? I'll call it VP, okay? And and then after that, after the final state, this is the initial. The final state is that another arrow was thrown away. So the arrow, but this time the arrow going this direction, okay? Is a 30-degree angle, okay? With velocity, I'll call it VA here, okay? Well, the person certainly will have a different speed here, okay? With the bow and everything. So let's call this VP prime. So, and this is it's a VP prime that we're interested. We know VP, which is already here. We know VA as well. It's the same as the previous case, but we want to find out VP prime, okay? Now, this one is a little bit more complicated because there's an arrow involved. And most of the problems you solve in your homework and the test problems are gonna be, no, we won't consider angles, but here I just want to use this as like an example. So when you have arrow, what does that mean? It means that, okay, so in the end, right, if you define this as your X direction and this as your Y direction, the momentum has two components. There's an X component, Y component, okay? The momentum, the total momentum is going along this direction, going along this 30-degree angle. So you need to use momentum conservation, but which direction does the momentum conserve, okay? Well, along the X direction, okay, remember, first of all, this conservation law is like this, right? So in general, it could be applying for both directions, but it really depends on whether it is conserved or not. Actually, in this case, along the X direction, it's the same situation as we had here. There's no friction, no external forces. So along the X direction, certainly it is conserved, okay? So you can say PIX equal to PFX, okay? But what about the Y direction? Along the Y direction, right? At the very beginning, there's no momentum, but in the end, right? This thing, the arrow goes up, right? Well, we have momentum conservation, the person would go down into the ground, but it's not happening. The reason is the ground will give a normal force to the person, so it kind of balances the person on the ground. So there's external force given by the ground along the vertical direction. So along the Y direction, the momentum is not conserved, okay? I'm sorry, PFY, okay? It does not conserve momentum. So only the X direction conserves the momentum, and that's actually what we needed, okay? So if you, that means for considering this case, we need to find out the x component of the arrow. So it's going to be VAX equal to VA times cosine 30, okay? Because that's the again, this triangle here, right? This will be VAX, this is VA. So this is definitely cosine 30, okay? So VA is 50 meter per second, cosine 30 is 0.866. So just go ahead and calculate it. You'll get, let me see. Okay, you got 43.3, okay? And that part is the part we need to consider because that's part of the momentum that's being conserved, okay? So now let's use the conservation momentum along the x direction, okay? Right, PIX equal to PFX. Now, in this case, you start from initial state where there's no, this is your final state, okay? The initial state has no momentum, sorry, there's already some momentum in there. So you write MP, VP, okay? Now the final state, you have both momentum from both objects. So I have MP, VP prime plus MA, VA, but I'm gonna write VAX here because VA itself is going along a angle. So only the VX is the part of the X component momentum. So we got this. Now, again, we want to solve for VP prime, right? So I will just move this term to the left. You have a MP VP minus MA VAX equals to MP VP prime. So VP prime equals to this whole combination minus MAVAX divided by MP, okay? Now you're plugging numbers here, okay? Okay, first of all, MP. Notice this MP is different from the previous case. The previous case is 60 minus 0.03, right? But now you have another arrow going out of it. So this MP is a little bit less than that. So again, notice here we're dividing the whole thing as two parts. The mass of the person plus ball plus our arrows, and then there's an arrow here going out of it. So this MP is actually going to be 60 minus 0.03 and then minus another 0.03, okay? It is the person without two arrows, okay? Well, the speed is, the velocity given here, right? Negative 0.025 meter per second, okay? And then we have, the second term here, which is MA, which is still 0.03 times, okay, let me put a kilogram here, times VAX, which is 43.3. Okay, like this, okay. And then we have a MP here, which is 60 minus 0.03 minus 0.03, okay? So that's the kilogram, okay? That's the combination. I mean, that's the expression here. So with that, we can go ahead and get the answer. So this is gonna be just 59.94, okay, kilogram, okay, times, okay, let me just go ahead and calculate, although I don't want to write everything down again. So 59.94 times 0.025, okay, that's this number, and then I'll add this to it because both of them are negative, right? So 43.3 times 0.03, okay, so we got actually 2.80. Let me use eraser here. Negative negative 2.80 kilogram times meter per second divided by 59.04 kilogram. Okay. So the answer is gonna be okay, 4.74 times 10 to the negative 2. 4.74 times 10 to the negative 2 kilo, this meter per second. Okay, use a minus sign. Okay, so again, the answer is negative because the person is gonna go even further to the left because shooting an arrow out of the bowl, and then it's definitely bigger than previous case because it started from this negative momentum and then it got a little more negative because they have some positive going the other direction. So roughly we got this number. Okay, as I said, the second part is a little more complicated because it involves the component of the momentum. Most of the problem you have in the homework is not like that. It's more like part one, but part two is useful because I want to show that not every case the initial momentum is zero. In this case, it is not zero because this one is already moving, right? So, but the idea is the same. You write all the total initial momentum and you write all the total final momentum, set them equal to each other. From there, solve the unknown. Okay. So this is negative 2.5, negative 4.74. Let's see. Let's check the answer here. Negative 0.025. Sorry. And then this is negative 0.0467. Yeah, that's right. Okay, we got a little bit different here because the way we run the numbers in the middle. So anyway, do we have any questions? We're good. Okay. Now again, this is the problem I want you guys to know how to solve. Okay. Well, today, let's see, we have another 25 minutes. What I'm going to do is I'm going to go ahead and do the next part of the last part of this lecture, and then we're going to finish this lecture, and we will finish this chapter, and then we might do exercise like tomorrow. Okay, so by finishing this, you can start to do the homework on this chapter. Okay, so